Okay, it's with great pleasure to introduce Peter Lumsdaine from Stockholm University, who's going to tell us about general dependent type theories. On to you.
Right. Thank you very much to OHAD for the invitation. This is great fun, and as ever with these things, it's sort of suddenly surprising and a bit shocking the audience one gets, that one thinks, it's a nice local seminar, you know, the normal sort of friendly audience of a dozen people or something, and then online you suddenly get 50 people or whatever. But right, so today, I hope, by the way, that everyone can see my slides. I guess, right, I'm used to Zoom where I can see the visual feedback from everyone else. I can't see your faces to tell if you're happy, but I presume you'll give me the feedback again, as I had said, with smiley faces or unhappy faces. Let's see. Several people are saying thumbs up, so I presume that means they can see my slides. One person said they couldn't see my slides, but if others are, then I think that means you may have to look for somewhere to click my slides rather to bring them up. Yes, so this is mostly going to be a fairly high-level talk. There are almost zero technicalities, or rather, there are quite a lot of technicalities, but I'm outsourcing them all from the slides. All the technicalities I'll outline a bit and then post links to places that you can read more about them if you want to read more about them. And I hope by the end I will persuade you to want to read more about them, because this is much more of a sales pitch than of a sort of normal, here are all the technicalities. It's a pitch for, firstly, a problem, a gap in the literature, which, like of sales pitches, that it's not as simple as some gaps in the literature, which are clear gaps. This is something where I suspect many of you may disagree over whether there was a gap in the literature, and I want to try and persuade you there was. And then, having convinced you that there was a gap in the literature, I will try and sell you on several proposed solutions of it, some of which I've been involved with, others by other people. And I think now, where a few years ago, I think there was a very unsatisfying gap in the literature, now I think there are several good proposals which between them give a very satisfactory solution to the gap in the literature. And I want to give a sales pitch for various pieces of work that give these proposals to fill it. And the gap in the literature I'm talking about is giving a general definition of dependent type theories. And by general definition of dependent theories, what I mean is dependent type theories, firstly, in the sense of things like Martin-Löf's type theory and its successors, the variants of it that have been studied since then. Martin-Löf originally introduced his dependent type theory, which was at least sort of one of the first dependent type theories to be introduced as a formal system. There had been non-dependent type theories before, and several other people also worked on dependent type theories at a similar time, but Martin-Löf's is, let's say, a canonical one to point to. And what am I thinking of it as? Thinking of it as a formal system with essentially dependent types is really the key thing that I want to just take it as an exemplar of. Specifically, it has 4 judgment forms. It has a notion of contexts, and over those your judgment forms are types, type equalities, elements of types, and equalities between elements of types. And then over those, it's got various different constructors and rules, logical constructors. The original version had a sort of a specific combination of a few things. It had dependent products, it had dependent sums, it had identity types, and it had a universe, and a few other things. And then lots of variants have been studied since. Martin-Löf fairly soon afterwards introduced sort of several other variants that had refinements or different combinations of rules. Girard pointed out the paradox in one of the early formulations with the universes, so the universe system was refined. And lots of other people since then have introduced more interesting type formers. You can add, many people in this room have introduced kind of interesting new variants. of dependent type theories. So, right, so there's lots of dependent type theories out there. Some of them are fairly close to this system in their presentation, with the same four judgment forms and essentially the same structural rules and things. Others have been generalized in lots of different directions, not just new rules and type constructors and things, but new judgment forms, different structural setups. And so, it's a kind of widely varied range of different things that one can think of as a dependent type theory. Lots of different things. And in many ways, one wants to think of it as a sort of an open class, like a programming language. It's not something that you want to quite nail it down and say, all right, here is what a dependent type theory is. Anything outside that doesn't count. It isn't a dependent type theory. The great thing of its flourishing has been how many interesting variants have been introduced, interesting directions of generalization, and so on. And at the same time, there are clear motivations for having some general definition. Not just out of sort of kind of sense of tidiness, but for the sake of some of the theorems that we want to prove and use about them. So here are a couple of important meta-theorems. The first is the initiality theorem. This is proved by Thomas Streicher in 1990, following other names I should mention like Cartmel and Pitts and so on, who'd been involved with earlier work, but Streicher's is a sort of particular version I want to point to where a specific version is carefully proved, saying that you take the calculus of constructions, which is a specific dependent type theory with a particular combination of logical rules in it, saying that its syntax, you can form the initial contextual category with, again, algebraic structure corresponding to those type constructors. What is a contextual category? I'm not going to tell you that. If you want to find that, you can look up Thomas Streicher's book. It's a good read. But I'm not going to tell you what it is and not going to care too much about the details of what it is. It's some kind of algebraic structure defined as a category with certain extra structure, certain extra algebraic operations, which correspond to the different rules and constructors of that particular type theory. And so this is an important and fundamental theorem that you want to use when you're constructing models of a dependent type theory in any models that come from sort of denotational semantics directions of structure that are kind of mathematical structures and things. Usually the cleanest way to present them is by this or some of the similar related techniques of some kind of categorical algebraic abstraction to which a general theorem like this then tells the initiality tells you once you've got an algebraic structure of this sort, then automatically you get the interpretation map from the syntax of your type theory into this structure. So you don't have to go into the syntax with all its details of variable binding and so on by hand and do your structural inductions all over again. You rely on a theorem like this that's nicely proved once and for all, gives a clean axiomatization of the algebraic structure you need to model the type theory, and so you can present the rest of your models that way. And for large classes of models, that's by far the cleanest way to present them. So it's a very useful and important meta-theorem that's been used many times since. Another theorem related to that, and often used together with it, is a coherence theorem. So this is a theorem that's due to Martin Hoffman from 1995 and reformulated slightly by me and Michael Warren, which is, again, a lot of black boxes in the statement. Any comprehension category with pseudo-stable ETT structure is equivalent to a category of families with strictly stable ETT structure. What on earth do all those magic words mean? ETT is perhaps the key one. That's extensional type theory. It's another of the type theories that Martin-Löf introduced as a sort of direct descendant of his original intuitionistic type theory. Extensional type theory, so it's a certain combination of Martin-Löf's logical rules and constructors. And then categories with families with strictly stable structure is something roughly the same as the contextual categories with logical structure that was in the statement of the Streicher theorem. And then the comprehension category with the pseudo-stable structure is a sort of slightly too categorically weakened version of this. It's something where certain equations that in the strict version hold on the nose, in the weak version they hold up to isomorphism. And so this theorem again is very useful for constructing models of these dependent type theories. That typically your mathematical model, simplicial sets or cubical sets or sheaves or whatever else, in the mathematical model, when you look at it, when you take it on its own terms, its things will commute only up to isomorphism in places. Streicher's initiality theorem tells you if you had something with the extra strictness conditions, then you would automatically get an interpretation of the syntax of type theory. This theorem of Hofmann tells you, fine, from your thing where things commuted up to isomorphism, there's an automatic way to turn it into one where things commuted strictly enough that you then get the automatic interpretation of syntax. So these two theorems together are kind of key for constructing models. But I don't want to, right, I won't be looking today at the, so much at the specific contents of using these for models or anything. The aspect I want to focus on is that each of these theorems was proved for some specific type theory. For so the Streicher proved initiality carefully for the calculus of constructions. Martin Hofmann proved this coherence theorem for Martin-Löf's extensional type theory. Is there a mismatch? Is that a problem? It's not a problem. We all know how to fix it because you read any of these proofs, you understand the proofs carefully enough, and it's clear that Streicher's theorem would have held with essentially the same proof for extensional type theory. Or Hofmann's coherence theorem would have held with essentially the same proof for the calculus of constructions once you formulate the statement right. And heuristically, a lot of people who've worked in the field, once you've worked in the field long enough, you get a good heuristic understanding for these two theorems and lots of other meta-theorems that are proved about some type theory or another, that heuristically they hold not just for the specific type theory that they are proved for, but for all reasonable type theories, and in some reasonable sense that we know it when we see it. We can look at, someone comes up tomorrow with a new kind of rule that they've added, a new clever kind of inductive type or something, and we can all look at it and agree, oh yes, yes, definitely, the standard theorems all extend to this type theory, that's clear enough. And then, of course, this is always a little unsatisfactory, to have a heuristic understanding of the generality in which some theorem holds, but not to have that heuristic generality made precise. And it's a little sort of unsatisfying in your gut as a mathematician, regardless of whether it's actually problematic. But as the theorems get subtler and as they're building more on top of each other, and as the type theories you're using them for get bigger and generalize in different directions, then it starts to be in danger of becoming a genuine problem where to really know whether it was valid to use Streicher's theorem for this other type theory that he didn't prove it for, kind of you need to have read and understood that proof fairly well to be really confident of where it does work. And enough people in the field who've been in the field long enough do know how it works, but at least for people coming into the field, when one's a new student getting to learn this, it can be quite hard to really be confident of which theorems hold for which type theories. Do they all hold for all type theories, or everything that anyone might call a type theory? Usually, I mean, we're all pretty reasonable, and then you don't know which is the slightly interesting, unusual generalization of a type theory someone gives where these don't hold. So there's a clear demand, there's a clear motivation for having a general definition of type theories. And then there's a clear, yes, sorry, yes, let me skip 2 slides ahead. Yep. There's a clear answer to this. There's a clear general definition of type theories, which was given by several people, including Martin-Löf fairly early on, which is the logical framework, which is an answer to this. And so the logical framework, sorry, I've lost, sorry, I skipped over 2 slides when I meant to skip over 1. Yeah. So the logical framework is that instead of understanding your type theory in the naive way, you embed it into a different theory. So right, now let me step back to the slide I skipped over. So the naive reading of a type theory, of something like Martin-Löf's type theory, as I set it up before, is that you have these syntactic expressions like some big type or term built up out of things. I mean, everything you do is with these. And that these are simply part of what one might call a raw syntax, which is something that has algebraic operations, but that also bind variables. And this thing comparatively well understood. There are different approaches to variable binding, and so on, and the equivalence between them is well enough understood, whether you use named variables or de Bruijn indices or de Bruijn levels or whatever. And then that on top of these expressions, you have the rules of the type theory, and that these are defining the derivability relation between the judgments, so that let me go back to the slide where I gave such a rule. The pi formation rule, it's simply a notation for the condition saying if the judgments on top are derivable, then the judgment on the bottom is derivable, and the derivability judgment is the smallest relation. Sorry, the derivability relation is the smallest relation on judgments closed under these closure conditions. You give 25 or so rules, maybe more depending on the type theory. And so this is what I'll mean by the naive reading of a type theory, that you have a raw syntax and then a derivability relation on it, inductively specified by the rules read as closure conditions. And the logical framework presentation of type theories, I keep skipping over the slide by mistake, there we are, is that you say, no, that's not what we take our type theories to be. That when we read that particular type theory, instead of setting up the grammar with just its things and that they bind things and so on, we start by setting out once and for all a fixed type theory, the logical framework, and it's a dependent type theory that's actually quite similar to the Martin-Löf's original one. It's got function types, it's got maybe strict equality types and things, and most importantly, it's got a universe, which we call the universe of types. And then of the theory that you actually wanted to set up, all of its constructors and rules are taken as constant symbols of some type, or equivalently variables of some type, some sort, within the logical framework. So for instance, pi, instead of, in the naive reading, pi types, dependent products, they were a symbol which had some variables and then had a rule, especially for the pi types, that said how they work. Here, we set up the original logical framework and fixed it once and for all. And within that, now, pi doesn't need a rule of its own. It's just a variable of a certain type which quantifies over universes and uses the function types of the logical framework in order to sort of simulate the variable binding. So you have the fixed logical framework as background, and then that simplifies what everything else later that you add has to be. Nothing else needs to introduce new binders and so on. Those binders can be encoded using the background logical framework function types. And so then any other type, and so then the whole type theory that you're trying to encode, your object theory, it's just a context in the logical framework. It's just a list saying, here's your pi, here's your lambda, here's each of your other constructors or rules. Question from Andre Bauer?
I maybe, hello.
Hello.
Can you hear me?
Yes, I can hear, but I can't see you, but maybe that's
deliberate. Yeah, it's just a very minor thing. I think maybe I'm trying to deduce this terminology from 12, the implementation of LF, but I thought pi and lambda here would be part of a signature, not of a context. I think that it's a very minor thing.
Right.
I just want to understand whether you find this in
uses the logical framework. Absolutely, yes. So you could.
Okay.
This is a part of
it's
the
just
context
terminology
think
here.
of,
It's not.
Yeah.
Okay. Thank you.
Yeah. Yes, and right, and one of the, a direction that I had considered saying a bit more about but didn't go into is that logical frameworks get used in various slightly different ways. So right, I am not sort of trying to say the be-all and end-all of how logical frameworks are always used at all, but I'm giving one of the ways that modulo terminology, you can see logical frameworks as giving a definition of a fairly general definition of dependent type theories. That once you've got enough background type formers, then the object theory you want to encode is simply postulating some variables or constants of certain sorts in the logical framework. So, is this a satisfactory answer? Obviously I'm going to say no in the end because I'm making a sales pitch for other answers, but before saying no, I have to say, no, clearly, yes, it's a really good answer. Logical frameworks are fantastic. They're lots of good and powerful work has been done with them. And also there are precise, so the thing which one might first worry about is it the same as the naive definition? We've said we present our type theory in a different way from what we originally thought we would using the logical framework. Is that justified? What if this presentation is genuinely different? It proves different things. And we've got a theorem, thanks to Martin Hofmann again. All of the best theorems in this sort of direction are Martin Hofmann, saying that the embedding from, I think he proves this theorem, if I remember right, for a version of Martin-Löf's intentional type theory, that the embedding from this type theory to its logical framework presentation is conservative in a very strong sense, that says that the things you can prove in one of these theories are totally equivalent, whether you prove it in the original or the logical framework presentation. And this is nothing special about ITT. This holds, again, for all the other sort of variant type theories that we could look at. This proof heuristically extends to all of the other variations we tend to study. And so this justifies that the logical framework presentation is a good alternative way to look at any individual type theory. And its big advantage over the individual ones is that it gives a general definition of a wide class of type theories that you can present in this way. So, but I'm obviously going to say for some purposes, it's not quite satisfactory. So one of the ways in which it's not quite satisfactory is a sense in which it's not quite general enough, that some theories for which the theorems that we wanted to give in generality, those meta-theorems I gave before, that we have this good heuristic understanding of what kind of type theories we can extend them to, some of those theories are not things you can represent in LF. In particular, certain infinite theories, which both do arise in nature, it's not too hard to find examples of them, and also, even if they didn't arise in nature, they so easily fit into our heuristic understanding of those theorems and their proofs that it would seem odd if the generality then excludes them just sort of because it wasn't ready to cope with something infinite. And sure, no problem. So one answer to this, and it's not a bad answer, is that you can extend the logical framework either by maybe adding some natural numbers to it so that it can define things internally, inductively, or by other infinity rules and things. And that both does cover them on an ad hoc basis. And then as a general answer, it's not that satisfactory because firstly, the whole point of trying to give the general definition was it was supposed to be something that was fixed in advance and didn't need further extending, to have a base theory that gave a definition that then was once and for all the definition. And on the other hand, also, as if one is extending the logical framework to cover these, one needs to also extend the coherence theorem, the conservativity theorem, to be confident that they do match up with the naive reading of the theories, which is, again, not automatic. Another is that the logical framework definitions are too general in other senses, that you have to cut them down, that it's certainly not a signature. A type theory should be an arbitrary, getting notifications from things to do with this coming on multiple devices. If I just mute my other devices so they stop buzzing. That it's, you want to cut down the context and say which ones represent type theories within the logical framework in a way that hews as closely as possible to the heuristic generality that we had in mind when we looked at those theorems and where we think that our understanding of them goes. And it's quite hard to delineate that one can delineate certain contexts to represent things, but to get it narrow enough that our understanding covers them without being too narrow, without ruling things out, seems quite difficult. And then philosophically, there's also just, this is something that always slightly bothers me, that I think it's hard to make the case that the logical framework reading is the natural reading of the rules of type theory. That I've heard some people, I mean, as with, let's say in categorical logic is another place that you see this, that you have a very nice alternate and equivalent definition of certain things, and then you persuade yourself that actually the equivalent is sort of more natural than the version you originally thought of. The version you originally thought of was too naive. And then sometimes that's satisfactory and sometimes it's not. This is a case where I definitely would argue it doesn't seem fully satisfactory. Because if you think that the natural reading of the rules of type theory is through a logical framework, how are you reading the rules of the logical framework itself? You can't say sort of read them in some higher logical framework, it's turtles all the way. You need to bottom out somewhere by having the logical framework, you give its rules the naive reading or something. So sooner or later one needs to come down to the naive reading of some rules as specifying a certain grammar and certain closure conditions, or if not necessarily that, but something else that doesn't then regress back to a further logical framework. So the logical framework is an extremely powerful and convenient and flexible device for presenting and embedding type theories. But I also want something that then covers the naive general definitions, and I think there's one also wants that for the sake of completeness of our understanding. And then finally, there's simply the pragmatic justification, which is just some of the meta theorems that I would really like to generalize. I can't see how to formulate and prove those within the logical framework embedding, and as far as I know, there are other theorems that people haven't managed to formulate and prove within the logical framework embedding. And so the one that particularly got me into this was my coherence theorem with Michael Warren, which was a slightly different coherence theorem from the Hoffman one I quoted earlier. I mean, it was just one that was slightly subtle to formulate in a lot of ways, and we couldn't figure out how to give a general formulation of it using logical frameworks, presentations of type theories. And so that got me sort of going on we have this heuristic understanding, we should be able to explain what kinds of type theories it generally, what kind of things we really have in mind. What is a precise formulation of the heuristic understanding we have? And so kind of summing it up, what we're after is, there's a question, I'll finish this slide if I may, and then take the question. So what we want, and this is where I wrap up the gap in the literature that I'm trying to pitch to you. We want a definition of dependent type theory that is, even if this is descriptive, not prescriptive. It's not supposed to say, these are the dependent type theories, stop doing anything else. Of course not. They're an open class, but it's supposed to try and delineate a large class of dependent type theories, which should, firstly, in specific cases, it should match as closely as possible. Ideally, we'd like some version that at least yields precisely the naive reading of type theories, and then other definitions would be great, but they should be equivalent to the naive reading, like we saw that at least in special cases we knew that the logical framework embedding was equivalent to the naive reading. Also, the practical motivation is to allow formulations and proofs of all these meta-theorems that we heuristically understand, to allow formulations and proofs of those in this generality. And that it should match our heuristic understanding of where those proofs hold and where they extend to. So this is the place where I hope to persuade you that there is a gap in the literature, that not that there's no definition of dependent type theories at all. There are lots, there are good ones, but that there's none that seem to quite fit these motivations, or at least none until recently. And the second half will be giving you the sales pitch for several of these proposals by myself and others for answers to fill this gap. Questions? Yeah, yes. Question from Brigitte?
Right. I was just wondering if you could explain a bit more what you mean by meta-theorems on your previous slide, because LF, as you also said, it's just a definition of constants, and then derivability, like typing rules, we can formulate as type families, and each of the rules will be another constant in the logical framework. But normally there's this problem that we can't really formulate meta-theorems directly in the logical framework. So I'm not sure on what level these meta-theorems for you live, because they don't live within the logical framework itself.
Absolutely, yes. So by meta-theorems, I mean the things like on this my second slide, like Stryker's theorem about the initiality and the Hoffman coherence theorem. And as you say, these they don't live inside the logical framework, or at least, right, for most of the ways that one thinks of and uses a logical framework, they don't. On most approaches to what a logical framework is, the logical framework, because one wants it to be a conservative embedding of the naive understanding of the theory, that just it's a way of presenting the theory that doesn't change anything about the theory. It wants to be a sort of thin skin around the object theory, as opposed to the kind of big meta theory, in which I mean the mathematical reasoning we're doing about the whole thing all the time. So sort of by meta theorems, I mean simply theorems about the object theory, proving them in whatever mathematical framework we're reasoning in the whole time about object theories. And the logical framework isn't what one's working within for that. The logical framework is this sort of, it's an object theory in itself. It's just a kind of thin, kind of wetsuit-like skin around the object theory one originally wanted to present. It itself is an object theory in some sense.
Okay, so is your so the meta theorems are something we would do on paper, like the coherence theorem at the moment, but your goal would be also to do these meta theorems in some other foundational framework.
The meta theorems, we do them and we do them on paper, and we can also do them. I mean, we can also formalize them in sort of a proof assistant, or think of them as formalized in type theory, but they have the same status as any other piece of mathematics we do. We're doing them about some mathematical objects, in this case our object theories, and they're in the ambient place we work mathematically, whether or not we're committed to that being any other particular foundational system or not. And so what I want isn't particularly linked to making that ambient meta framework more or less sort of formal. What I want is more within that, whether one's thinking of it as happening on paper or in a proof assistant or whatever else. I would like to be able to give these meta theorems as a general statement about a precisely delineated class of type theories, not as a specific ad hoc statement about one type theory.
Okay.
And for some statements like that, some statements like these, the logical framework is a very good way to let us do that, because we can say by a type theory we mean a certain kind of context, a signature defined in the logical framework, and we can prove once and for all about the logical framework and things it has, that things are well behaved in certain ways and so on.
Okay.
And so for a lot of meta theorems, the logical framework gives an excellent definition of type theories that allows one to prove them the way that I'm saying I'd like to. But for these particular ones, it doesn't give quite the formulations that I would like to get.
Thanks for clearing.
Yes, is that? Yep. Great. Where was I? Yes, thank you. So yes. Now, which slide? Right. So yes. So this was the desiderata that I wanted to set up. Thank you for that question. Any other questions before moving on to the proposed solutions? Right. And so this was a kind of question that I got into about 6 or 7 years ago on that theorem with Michael Warren that we really wanted to generalize and couldn't give the general statement because the framework didn't exist for stating it generally. The right definition of a large class of dependent type theories wasn't out there. So I've been on this for a while, sort of thinking, working slowly about it, and then it's been a bit recently the sort of, you wait all that time for a bus and then 3 come along at once. That in the last few years, there've been several proposals, and I think all sort of good in different ways that fill things very close to this gap in the literature. And so I want to give, what I'll give for the rest in the next 10 minutes or so is a quick overview of these proposals and the different kind of amounts that they cover this bit of literature, and then I'll give you pointers to more details for them. And so some are by Andre Bauer, who's here, Philip Hasselwater and myself working together. Some are by Guillaume Brunery, some are by Valerie Saev, and some are by Taichu Uemura. So the first one, or the first two rather, that I'll mention are the one of Andre and Philip and myself, and of Guillaume. These have both been not written up, I'm afraid. They've both been sort of in progress writing up for an embarrassingly long time. But there is one place you can go if you want to see more details, which is that there's some slides on my website from the Scandinavian Logical Symposium in Tampere on them. Except I thought there were, and then I went to the link I thought they were at on my website earlier, and the link was broken, and I didn't manage to get it fixed because I was trying to sort out the technical issues in my slides. So there should soon after this talk be on my website slides where you can read the details of this, or an old version of this at least, if you want. And these approaches, they take the naive approach very literally. They formulate, so they say you take your basic raw syntax as a signature in the sense of a grammar with variable binding. And then you say rules are notations for certain closure conditions, derivability relations are inductively generated by those. And then you try and formulate, all right, but we don't just allow sort of random selections of closure conditions because that would be badly behaved. You try and isolate what are the conditions on the signatures and the systems of rules that we have in mind in order for our heuristics understanding to hold up, for things to be well behaved. So these are kind of quite naive definitions and approach, very, very concrete and pedestrian in a way. But the nice thing about these is that they match they recover literally the naive understanding of a type theory, the naive reading of a type theory. When you look at what they give in ad hoc cases, they don't rely on checking that it's equivalent to anything else or a conservative embedding of anything else. The limitation I should mention of these, or at least of the versions of them we have so far, is that we haven't got them generalized to different judgment forms. Both our group and Guillaume have them set up simply for the sort of fixed collection of judgment forms of Martin-Löf type theory. And one certainly should be able to generalize them to other judgment forms, but that's again a little tricky to formulate. The next pair of definitions I want to mention are ones that are myself, again, in preparation, no published version yet, and then a version published, or I think it's published now, certainly at least pre-printed version from Valerie Saev in 2016, which use the categorical semantics that I referred to earlier through the Stryker theorem, which is to say they're contextual categories with certain extra structure, and then you have to isolate which kinds of certain extra structure make the extra structure and contextual categories behave the way you expect a type theory to behave, in ways that then let you prove the theorems about them that you would hope should hold for all these type theories. And so, right, so it's certain essentially algebraic theories extending the theory of contextual categories. And then within that you can, right, to explain the last bit here, I should go back to the previous slide where I skipped over something. So one of the other ways that we can understand the kind of naive presentations of type theories, the traditional by hand way of writing a type theory with rules, one can either read it as there's a raw syntax, and then there are rules, and you look at the connection of rules afterwards and check that it holds up well. Or you can think of it as that the symbols of the signature are presented at the same time as the rules are. That sort of, it's not like we start by saying we have the symbols and the raw syntax for pi and lambda and sigma and id and so on. It's so we introduce the rule for pi types and the pi symbol of the raw syntax together. Then the sub lambda and the rule for lambda are introduced together. And you do this in a well-ordered or well-founded way, and as each individual rule is introduced, you check it's good, and then you expand the signature and expand the type theory. So that one of the ways one may want to analyze presentations is as being well-ordered in a certain sense. And this version, and that shows up in the essentially algebraic approaches as having a sort of cell complex extensions of theories. And so these two are somewhat, they're both, I think, with apologies, I hope Valerie doesn't mind my saying this if he's here, but I feel this for both his and mine that are along these lines and fairly closely related. They're kind of a quite close description, but they're a bit clunky as a description of sort of what the categorical incarnations of these dependent type theories look like. And then the Taitu Omura ones, which is newer last year, that was, sort of reading that was one of those, damn, I wish I'd found this moments. It's a really, really lovely, and I think much cleaner abstraction of what's going on in the categorical incarnations of the theories. And it's also much more general. So he gives, this again is not one approach, but two. He both gives a categorical approach using representable map categories, and then a syntactic approach, which uses something which, this isn't his phrasing, this is mine, but which I would view as a sort of, it's a double logical framework embedding of the type theory. And so the double logical framework embedding and the kind of in parallel the representable map categories. And the syntactic version, the sort of double logical framework, is also a kind of extended logical framework within a pure type system and with some transfinite rules added. So it's a somewhat sort of, when you first see it, one to look at. But it really very nicely isolates, I think, the heuristics of how we present type theories. So this on the archive, I can't recommend it too highly. There's both this categorical incarnation and this syntactic presentation, and he shows that they're equivalent to each other. Right, it's much more general in that it covers most of the kinds of, most of the extensions that one can give by different judgment forms and things. And then the one thing which makes this, I think, in itself not quite an answer that fully fits everything that I was asking for in the Desiderata, is that neither of these are terribly close to the naive reading of the type theory, to what one gets for the type theory as one reads it in a specific special case, and as one would read and set up each one on its own right. But with the when one can compare this to the formulation by Andre and Philip and myself, where we give this, and Guillaume, where we give the naive reading and make that precise in a wide range of generality, And in those cases, one can show that matches up with the Uemura framework. So, right. So overall, this is, insofar as I'm leaving with a sales pitch for anything, it's mostly not for my own work. Sorry, Andre and Philip. It's mostly not for our approach. It's more for Uemura's approach, but also partly for our approach, which I think helps by showing that the naive reading of type theories matches up with these more sophisticated, high-powered frameworks. But the Uemura gives an extremely clean, extremely powerful and general framework for presenting a very large class of dependent type theories, and in a form which seems to be pretty well suited to extending, emulating the meta-theorems that I started out by mentioning. And that's where I want to wrap up. So I think thank you very much. And there's a question from Paul, but I guess I'll say thank you first and then take that in a moment. Yep. Great. So Paul.
Hi. Oh, sorry. Only I can clap because then. Oh, hang on. What's just happened? About to start video. Oh yeah, share video. Right. No. Okay. Allow. Sorry. Yeah. Anyway. So you said here that the Uemura approach uses a double LF embedding.
Right. I mean, that's my sort of rough gloss of what's going on in its syntactic approach.
Okay,
that's
so it's not. I mean, you made these criticisms of the use of LF earlier in the talk, but then that's not going to cause a problem if now you're using LF for setting up the syntax here.
Right. So I had, let's say, 4 reasons why I felt that the traditional way LF is used is not a fully satisfactory answer to my desiderata. And 3 out of those 4 are solved by the way that Taichi has kind of beefed it up, or the things he's done in it. That he refines it a bit. And the sort of double LF embedding, okay, that's a slightly bad phrasing perhaps. It's a sort of LF embedded within a pure type system. Right. I won't try and sort of describe it in detail, but he first extends it with a transfinite construction rule for signatures, which then kind of explains, I think, better than any previous approaches I've seen have the way in which the way in which infinite theories do work and ensure their well-formedness, and on the other hand, the way that it's within the pure type system, the sort of specific pure type system, gives a good. I mean, it's kind of the way of embedding type theories into it is what is slightly different from any previous uses of the LF I've seen. The way that the type theory is embedded in is just a little bit different, in a way that then makes it fit better and means that it does seem to carve out the generality that one heuristically wants more cleanly. The desiderata that Uemura's framework doesn't give, that I mentioned as one of the things I was unsatisfied with in the LF, is that it doesn't recover quite so closely the naive understanding of a type theory, and so that's where I think there's a sales bit not just for Taichi's version, but also for Andre and Philip's and mine and Guillaume's, which let one connect that make precise the naive reading of type theory in a big generality, and that one can connect those to Taichi's framework and show that those two do agree. So, yep.
Okay, thanks.
Yes. Yep. And Nathaniel Arkle?
Can you hear me?
Yes.
So I just wanted to clarify. So my understanding of Uemura's framework was that he has a logical framework himself, which is a type theory, and he describes this in section 6 of his paper. Mm-hmm. And so what he's doing is describing a categorical framework for this logical framework. Mm-hmm. But it seems to me that all the objections you had with the like Edinburgh logical framework would apply to Umara's, unless there's a reason that you think his is more natural in some way than Edinburgh LF. So do you have a reason why you think his LF is better?
Right. It refines it in a way that maybe that someone has given this sort of extensional refinement to the Edinburgh logical framework before, and I've missed that. But he refines it and extends it slightly in ways that I haven't seen done previously. So, in particular, the first big one is the way he gives the transfinite extensions, and the way that he uses it is that he has the logical framework. Its universes of sort of tie and term or whatever are happening within what's the notation he uses? A star and box or something from pure type system notation again, as I remember. Right, I'm forgetting the notation now. But in a way that then makes it more flexible for extending different judgment forms without requiring extra extensibility of the base system. And then, as I said to Paul, one of the things that I had as a limitation of the traditional logical framework, that it doesn't connect to the naive reading of Taichi's, I think does still hold, but the others don't. Sorry, Randy is pointing out that Edinburgh LF is not Martin-Löf LF, and right, I've been aligning that distinction. What I specifically wrote, I had Martin-Löf's LF in mind. The Edinburgh LF, I thought that most of what I said applies for that as well, and then I may be misunderstanding because that's not one I know as well. So if anyone wants to clarify on that connection, then anyone who wants to jump in, please do. And I guess the other thing that I suppose, where's the slide gone? The other thing that I would simply say is the big difference is the pragmatic one, that I can see that kind of reading the way that Taichi sets it up with that LF, it's clear how to formulate something like these coherence theorems using that setting, and that isn't so clear to me how to do it using Martin-Löf's logical framework or the Edinburgh one, as far as I know it. So, right, it's a pragmatic one. It's reformulated in a way that makes it, at least to me, much clearer how to do the things I wanted to do. So. And right, Andre has his hand up.
Can you hear me now?
Yep. Oh, you can see you now as well.
I'd just like to add one little item to the list of things explaining why you would want to have these basic pedestrian ways of treating syntax for type theory that I think that is needed if you want to implement any of this stuff, because it's all fine and well to do meta theorems in some abstract way, and I think that's the right way to do them, but implement, get down to the gritty details of syntax and did the user enter a rule that is acceptable, and so on and so on. And so at some point you need to do that. I expect in the future it's going to be less important because we're going to have better tools, and maybe everybody from kindergarten onwards uses dependently typed languages and says, well, we don't have to bother with non-dependently typed languages, just like nobody has to bother with machine language at this point, mostly. But I think at this point in history, we really that is a significant motivation.
Thank you. Philip Wadler?
I was trying to turn on my video there. Didn't.
Oh,
yes,
hello.
It worked.
Great.
Thank you. That was a really nice talk. And I want to especially thank you for not just advertising your work, but other people's work. I think that's a very constructive thing to do, and I'd like to encourage people to do more of it. So thanks for doing that. This is a very basic question, because I'm not an expert at this sort of thing. I'm just wondering where Barendrecht's pure type systems fit in here. I'm guessing that they're susceptible to some of what you said about LF, but...
Absolutely. So essentially, the same things that I said about LF. I didn't mention the post-site system because there are enough differences of detail that sort of getting into the specifics, everything comes in a slightly different place. But the same issues of why they don't far out a generality feels like a exact understanding of some of the theorems. The same general issues apply. Yeah.
So one of the things you said is, well, there are too many of them. I'm not sure that applies to pure type systems in the same way.
Sorry, too many of them in which place?
Sorry, the slide you had about problems with LS, right?
Yes, the two general side. Yeah.
Yeah. So that one, I would say, perhaps does not apply to pure type systems, and maybe 3 as well, 4 certainly could do. And if we go back to your 1, I think that one might as well.
Right. Yes, I think. Yeah, these I think aren't so much the too many. Right. It's more that again they don't seem, or at least I've never seen or been able to work out a way of using them to sort of delineate the generality that seems to fit our heuristic understanding of the theorems that I'd like to have general versions of.
Could you just go back? I want to remind myself what your point 1 was.
Point 1 was being not general enough.
Right, but that not general enough. Ooh. Oh, right. This was the point about infinite theories and the like. Yes, so that.
Right, infinite theories being one example. Yep.
To pure type systems. Okay.
Yeah.
Okay, I think that answers my question. And roughly what I was taking away from what you said about the last theory was that the right way to do this is just come up with the right categorical generalization. In other words, what any category theorist would tell you off the bat, but the problem is knowing what the right one is quite difficult.
Let's see, I'm not quite sure I mean to suggest that I see it that way. I don't think there's quite any one. I don't quite think this is something that should have any one right answer, but one, not the one right answer, but one of the right answers, one of the very nice answers is this categorical generalization that's given by Uemura. But I think it is also very nice both that he's given this syntactic equivalent formulation of his categorical one, and then that it isn't so close to the naive reading. It is, in a couple of ways, further from the naive reading, but insofar as we've looked at the comparison so far, the formalization of the naive reading that Andre and Philip and I have got seems to match up very well in many ways with Uemura's approach. In particular, he has this transfinite, his syntactic system allows transfinite extensions of signatures, and that modulo sort of converting between sort of well-founded orders and linear well orders and issues like that fits with our analysis of well-founded presentations of type theories by giving acceptable rules in some suitable well-founded way.
Right. Okay, I can see Randy wants to ask a question. I'm sure his will be much more interesting than mine. Thank you.
Thank you.
Okay. Am I coming through?
I'm getting the audio. I'm not getting video. So
Yeah. Okay. I don't have a camera on this screen.
Yeah.
So I think for first place, we shouldn't get confused here. Let's not talk about pure type systems at all, because they're really a fixed framework with some parameterization, and they're very far from a natural understanding of most of the theories that can be represented. So they use many levels of types, for example, to represent smaller levels of types, and they're not very general in the sense that Peter is talking about. So let's leave that aside.
I guess,
Unless someone,
if I may interject, I guess,
yeah.
right, the pure type systems, they both are and aren't general, I feel, in the same way that the logical framework, in one sense, it's not general because it's one specific type theory, but you can use it for embedding others, and as such, it can give a general presentation of others via embeddings. And so the sense in which the pure type systems are general, I think, is in the sense that they can be used to present ones in which one can embed other type theories. But right,
Okay,
they're general via embeddings, not directly. Anyway,
so that's true, and furthermore, you can prove meta theories in general using pure type systems. But my point is that it's very restricted compared to the notion of extension that you have been talking about. Now, as far as the Edinburgh logical framework is concerned, it doesn't have enough computation to represent strong dependent type theories. I mean, it never did. It's a big challenge to represent LF inside itself, even though it has no more forms than simple type theory. There's lots of people on this list who might have something to say about that, but I just confused. I mean, you were talking about a really interesting notion of generalized dependent type theory, and to get confused with these specific things doesn't seem like the right thing. So stop.
Right. Yep. Thank you. Yes. Thank you. Yes, I think that I'm not sure there was quite anything there to answer as a question, but thank you for a very good and detailed comment on some of these issues from another angle.